progress.
So it's my pleasure to introduce Ayman Badawi. I don't know if the pronunciation is correct.
Yes, that's correct.
Thank you. From the American University of Sharia. So this is the second opportunity to say something wrong. Okay, he's going to speak on von Neumann regular and related elements in commutative rings. Please.
Okay, thank you. First, I would like to thank the organizers, in particular our friend Andre, for giving us the chance to get together. And, I'm teaching summer school, so I miss many of the early morning talk. I think, I finish around 5 or 4. United Arab Emirate time. Anyway, so I only have time to attend the evening talks. Okay, so this is like an old paper written with my colleague and friend David Anderson, but I don't remember that I ever spoke about this paper in any of the meetings. So I thought this will be my chance to do that. Okay, so all my rings are commutative. And, this is like a reminder what we mean with von Neumann regular element. An element A in a ring, we call it von Neumann regular element if satisfy this condition, like a square x equal a for some x in R. I think most of you are familiar with this definition. And then we have pi regular element of R. What do we mean? If a to the 2nx equal a to the n for some x in R, an integer n bigger or equal to 1. And of course, you know what I mean with the idempotent of R, all the elements, Here, V in R, you need to follow this notation. This is just the elements in R, A in R, where A is a von Neumann regular element. So V in R are the elements of the ring that are von Neumann regular elements. And also you need this definition, so you follow my talk, what I mean with pi RR. Pi RR. And this, all the elements in R where A is pi regular. So we're talking about two set of elements. V in R mean the set of all von Neumann regular element. And then we have another set, pi RR is the set of all pi regular. Okay? Okay, so let's get to some of the result. Well, some of these are, I think, maybe known. Maybe 4 and 5 are not clear. I mean, maybe 1 and 2 and 3 are known in the literature, or maybe not. But 4 and 5, not many use 4 and 5. I mean, from my experience, does not mean I'm correct. So what these are equivalent conditions to von Neumann regular element. So when I say A is a von Neumann regular element, this means A square U equal A for some U in unit, A equal E times U for some unit and some idempotent. It means AB equals 0 for some B von Neumann and A plus B has to be a unit. And look at the fifth condition. All these conditions are equivalent. That, excuse me, just a minute. Excuse me. Hello? Excuse me.
Yeah.
Can you? Yeah, my family is talking, so I'm trying to tell them to slow down. Sorry about that. Not you.
Okay.
Yeah. Uh, okay. Here I said if A is a von Neumann regular element, then we know that from the definition. And you need to observe that X need not to be unique. And that's very clear. You can select Y to be an X plus the annihilator of A square, then definitely Y, A square Y, uh, sorry, A square X, Y, yes, exactly what I said. It will be A, all right? So this X need not to be unique in general. Uh, but the following result is well known, and I will share it with you. What does it say? Let R be a commutative ring and A be a von Neumann regular element. Then there is a unique X with this property. A square X equal A and X square A equal X. So we have uniqueness for X if the X satisfy these two together. But A square X equal A alone, then X need not be unique. Okay. Okay, so now we know the set, that's very clear, the set of all von Neumann regular element, intersection the set of all nilpotent element is 0. So it's natural to ask when R will be the set of von Neumann regular element union the set of nilpotent element. And we have an answer to this question. So my ring will be just union of two sets. Each element in the ring will be either von Neumann or nilpotent. And here is the result. R is the union of von Neumann regular element, union the set of nilpotent, if and only if either R is von Neumann or R is quasi-local. Quasi-local means it has exactly one maximal ideal. Maybe some of you use local, but for me, I use local when the ring is Noetherian and has one maximal ideal. I think this is the notation of Gilmer, quasi-local. Okay? And here, look at number 2. R will be the union of von Neumann regular element, union the ZR, the zero divisor of the ring. The zero divisor of the ring. R will be the union of these two sets if and only if the total quotient ring is R. So R, its own total quotient ring. And this is if and only if. Okay. This is kind of not surprising when you see the proof. In fact, it's not difficult. This result tell me to check whether your ring is von Neumann regular ring. You only need to check the zero divisor of the ring. But here we have very, the zero divisor of R need not equal to zero. So I take away the integral domain. So R need not be integral domain, because in this case, zero will be the same as this is the only zero divisor. So here, this result tell me, let R be a commutative ring such that the zero divisor of the ring is not equal zero. Then the zero divisor in von Neumann, if and only if R is von Neumann regular ring. So that means if you have a ring and it is not integral domain, to check if this ring is von Neumann, you only need to check for the zero divisors. Okay? Of course, this result is very clear if the ring is finite, because, each element in a finite ring, either a zero divisor or a unit, finite commutative ring. Okay, this result here by D.D. Anderson and Camillo, they prove R equal the union of unit, the set of all unit, union, the set of all idempotent, if and only if R is a Boolean ring. This is well-known result by D.D. Anderson and Camillo. So the question, why did I mention it here? Look at this result. Let R be a commutative ring. Then R will be equal to the set of all idempotent, union, the set of all nilpotent, if and only if R is Boolean. So if your element either idempotent or nilpotent, then the ring has to be Boolean ring. And of course, you get this result similar to the one before. If you have a ring that is not integral domain, then the zero divisor of the ring are subset of the idempotent if and only if R is Boolean. Okay, this is, to my knowledge, still a conjecture. Maybe it seems trivial, or maybe some of you know how to prove it, but for us, it's a conjecture. What's the conjecture? That if the ring R can be written as the set of all idempotent union, the set of the zero divisor, then R has to be a Boolean ring. And why do we conjecture that? Many reasons. I will give you some of these reasons why we feel that this has to be true, unless somebody can come up with example or prove it. Okay. So here is where this conjecture is true. If, some feeling to the conjecture, let me put it this way. If R is the union of the set of the idempotent, union, the zero divisor of R, then we know what are the unit of R. Only one. That's the only unit. That's very clear. Characteristic of R has to be 2. The nil of R has to be 0. The Jacobson radical has to be 0. And the total quotient ring of R has to be R. If R, so this is like, that's why we have the feeling that this result should be if and only if, in a way, because Boolean ring satisfy this condition. Nil of R 0, the Jacobson is 0, the total quotient is R, the characteristic is 2. If either the dimension of R equals 0, and you know what I mean with the dimension of R, 0, there are many definitions that mean R is pi regular ring, or every prime ideal is maximal. That's what we mean with dimension 0. Every prime is maximal. And R has finite number of maximal ideal, then R will be the set of idempotent union the zero divisor if and only if R is Boolean. So 1 and 2, we develop a feeling that we should have a theorem that R equal to the union of the set of all idempotent and the set of all zero divisor if and only if R is Boolean. But to my knowledge, we don't have a proof. I mean, neither I nor David. But we have some feeling about this result. Okay. The next one. Am I doing okay on time?
In theory, this is I mean, you started, if I remember well, 3 minutes late. So you should have 2 more minutes, but I guess we can be generous with a couple more minutes.
Okay, thank you.
2 or 3 minutes.
Okay, I will try to finish. This is like a result back to Ehrlich, I think. I'm sorry about the name. When an element is the sum of 2 units. This is very similar we have to these things. And maybe I should move. I think I have 24. I was like, I thought I will go fast. Let me tell you what. Yeah, I mean, okay. By the way, this paper already published, and we studied, like, we consider many questions, and we look at ring extension, and we studied like a clean ring, another definition, and we studied something called von Neumann local ring. That definition was given by Contessa, M. Contessa, I think that's the name. Just give you the definition, what we mean with von Neumann local ring. It means uh, if either A is von Neumann regular element, or 1 minus A is von Neumann for every A in R. We studied this concept too in this paper. And this concept, von Neumann local ring, been studied by Contessa, by Abu Isba, Henriksen, Acclam, Smith. It's a very nice concept, and we have some result there. Like here is, but okay. And then, we studied a clean ring, and I think this concept is known to many in either in commutative or non-commutative rings, in fact. Nicholson started this definition, what we mean with a clean ring. If for every A in R, A can be written as a unit plus idempotent. Until now, I see papers on clean rings, and they generalize that. Semi-clean rings, strongly clean rings. There are many concepts related to clean rings. So we study this concept too. There's no time to talk about it. And also we studied the graph. We call it the idempotent graph. So in fact, this paper is like 24 pages. So I think I stop here, and I'll tell you, if you like to get the full paper free of charge, this is the location. If you like, you can write it down, or you email me and I will send it to you if you like to know more. Okay, and here are some references. And I thank you.
Thank you very much. Thank you for your talk. I think so. Thank you for being so generous with papers. Yeah. So please